very well. He's been to my ranch in Montana, and I have a collection of about 40 pieces that you'll see a few of them here. So it's certainly my pleasure to be here, and thank you for the invitation. I'll give you a little background on myself. 1966, I graduated with a degree in engineering from California Polytechnic State University. That was spring of 66. In October of 65, Caterpillar came on campus and interviewed, and I took an interview, and they subsequently invited me to come to Peoria for an interview, a 3-day interview between Christmas and New Year's, which I did. And then in late January, I received a written job offer, and in about 2.5 seconds, I accepted it, and long story short, I landed in Peoria in July of 66. The way CAT handled new employees of that time, future management employees, was they set up very formal, very well done training classes. And I happened to be in class number 16, 14 guys, all but 2 of us were engineers, and nobody was from Peoria. I had had a total of 3 days total knowledge of Peoria, Illinois. So here we were. It was just about like joining a fraternity all over again. 14 guys, all single, didn't know anybody, and we just had a wonderful time. That training program lasted about 6 months, and then I was assigned to the product division sales engineering group, and I was titled Sales Engineer Vehicular Engines. So that permitted me to really get next to engine engineering, to be specific, at Caterpillar, and it was quite an interesting run, being out of school, idealistic and all of that, to walk into a sea of engine engineers, probably 80 drafting tables strewn all around, and to see how those men organized themselves and developed a new product or made major changes to an existing product. It was quite fascinating, and I learned the whole bill of material systems on how all of that worked at Caterpillar, and it was an extremely well-organized, developed system. From there, I went to the product division, to the scrapers section. So I worked with scrapers primarily for the next 2.5 years, and we did everything relative to scrapers, recommended new designs, changes in designs, tried to figure out what the market really wanted, problems that we had, so on and so forth. So I really got next to scrapers. Then in '69, in September, I was transferred to Denver, Colorado. We had a huge emerging mining market out there. You had the U308 uranium mining in Wyoming happening, huge coal fields, northeast Wyoming and south central Wyoming, as well as western Colorado, and we had bauxite and iron ore and everything going on. And I probably had 3, maybe 4 clients in that neighborhood that owned upwards of 150 large cat scrapers. So I was right at home with all of this, and it was a fascinating period of time. What I'm going to do this morning is start out with you, and I'm going to describe World War II and the equipment that was in the war, post-war what happened fairly immediately, what new products were introduced in that post-war era, primarily in the smaller sections of equipment. But the real thrust of my talk today is in the neighborhood of earth-moving systems. In the 50s, you had this big market emerging for big dirt, and systems, as they were developed. But then in the late 50s, you had a massive, massive overhaul that I will describe to you. So let's start with World War II. The Caterpillar line in those days was really quite small. You had 6 engines. You had the D3400, a 4x5 4-cylinder, the D4400, which was a 4 1/8 by 5 1/2 4-cylinder, the D4600, which was a 6-cylinder, same bore and stroke, and then the next unit out, there was 3 5 3/4 by 8-inch bore and strokes. This is the D8800. This happens to be a World War II veteran. I modified it a bit. It did have a genset on it, and this engine in particular served on a destroyer with a standby genset. There was a six-cylinder version of this, the D13000, which also powered the D8. And then there was a third engine in that family called the D17000, which was CAT's first entry into large industrial engines, this one being a 60-degree V8. And I want you to remember this engine later on in my talk. This engine was 126 horsepower, 900 RPM, which was synchronous with 60-cycle AC, and it produced 126 horsepower at 900 RPM. It weighed 90 pounds per horsepower. Keep that in your mind. So you had six engines, you had five crawlers, track-type tractors, the 5J D2, you had the D47J, and you had the 4R D6, and the 4T D7, and the 8R D8. And then what was left, you had three motor graders, a 212, 112, and 12, the very famous old 9K. I always was wondering why, as the number got bigger, the motor grader got smaller, but that's kind of the way it was. And then you had a bunch of dogs and cats. You had some pull-type scrapers, pull-type rippers, cable control units, things of that sort. So that's really what the World War II lineup was. Not as many machines and products as you might think. It was a very interesting time for Caterpillar, 1940 to 46. What happened, of course, is we went into the war. Cat was kind of unique in the sense that most companies, take Buick Motor Car Division of General Motors, quit building automobiles and shifted over to building parts for radial aircraft engines. Quite a degree of change. At Caterpillar, all they did was change the color of the paint from yellow to OD, and that was it. And they maintained production as hard as they could. Cat equipment went to three places: U.S. Army and Navy, Lend-Lease Russia, and Lend-Lease UK. That's where virtually all machinery went. And you have to remember, engine-wise, during the war, there was no power grid anywhere that the U.S. Army or Navy went. Everything was diesel gensets, and these guys were the primary source of power for both the Army and the Navy. So engines were very critical. Nothing developmentally happened during the war. They, of course, didn't quite have the engineering staff to make it happen, but they certainly didn't have the manufacturing capacity to do much change to equipment. And you really didn't need to anyway, because instead of years, equipment life was measured in weeks. And so all they were after is production, get them out of there and over here as quick as you can. What they are almost doesn't matter. So emerging from World War II, these three engines were the only thing retained in the Caterpillar line up until about 1955. The 5J D2 became the 5U D2. The 7J D6 became the 9U D6, a very, very famous old tractor. And then, of course, the 4T D7 became the 3T D7, which was a very famous tractor. This is one in my collection. And then that tractor, the 3T, at about 115 horsepower, became the 17A, which was rated at about 150. The key to the 17A, this was the first change from those three World War II engines, the 5 3/4 bore by 8, D8800 and the D13000 were upgraded to the D339 and the D342. This was Cat's first D339 application, 155 horsepower in the 1787. The rest of the line, I'll skip the D8 right now. The rest of the line, basically the motor graders is about what was left. The 212 and the D2 were discontinued in 1957, and the 112 stayed in the line, was upgraded, and it hung in the line until 72 when the G series came out. The number 12 was what really made a lot of change. It went from the 70 horsepower 9K in World War II, was upgraded to the 8T, which was a very, very famous, popular motor grader. And to show you how many of them were built, all of you probably remember the dry clutch, and then it went to the oil clutch in both the 9U and the 8T. That happened in the motor grader line at serial number 16,000. So that'll give you an idea of how popular that 8T was. Through the 50s, it grew to be the 70D and the 99E. And then into the 60s, the 99E was relabeled the 120. And that's when the 12F and 14E came out. And it was Caterpillar's budget motor grader primarily for the governmental market. So that's kind of a history of what happened to the existing lines in World War II. During the 50s, two new major product lines came out. One was a track-type loader, started with the HT4 and the number 6 shovel sitting right over here. It started with traction options, and then a loader tower was built. You came out with the 933, which was a new loader tower, but all D2 componentry. The 955, same thing with 7U componentry. The 977, same thing with 9U componentry. And then in addition, sitting right out here are three examples. You had the initiation of the wheel loader line, wheel type loaders, WTL is what we call them. 922, 944, 966 straight frames. Subsequently, in the late 50s, out came the 966B articulated, which changed the whole concept of a wheel loader, and followed by the 950. So that's a pretty good summary of what happened in the smaller equipment during and post-World War II. The real key to it, if you remember, there was only one wheel type scraper early in Caterpillar's life, and that was a DW10. I'll learn to work this. When you got into the 50s, and you saw some nice examples out here in this demonstration area, one of the main keys for dirt moving was a track-type tractor coupled to a pull-type scraper. Cat had a full lineup of cable scrapers and had them going all the way from the D2 through the D8. This is an example of a 14A D8 pulling probably a number 70 or something. Very, very popular tool. Number one, it had work-alone capacity. And number two, it was called in when you moved dirt further than a dozer could push it. So it was a short haul, work alone, small job machine. But it was slow, productivity was not all that good, and new products were needed to handle earth-moving systems. Think of that term. So along came the first serious entry into this arena. This was the original 6W DW20, a machine designed to go approximately 30 miles an hour. The bowl size typically was in the low 20s, and this was introduced with a brand new D3 to 37 engine. And what was most unique about this engine is this was Caterpillar's first entry into artificial aspiration, meaning an artificial air supply forcing air into that intake manifold. And this unit had a Roots type supercharger installed on it, but the problem with the supercharger was kind of basic. It was driven off of crankshaft horsepower, so it was a parasitic loss to the output of that engine. Even though it increased the air supply and you could increase the fuel supply accordingly and get a bigger bang out of that cylinder on that unit. I'll make a remark right now relative to supercharging versus turbocharging, because that was a big, huge innovation and change in diesel engine performance. And the key was this. A supercharger was a parasitic loss. A turbocharger was not. And what happens in diesel engines, if you take a cubic inch of fuel, 33% of that heat content of that cubic inch goes out the stack, 30%, 35% goes out the radiator, and roughly 34% out the crankshaft. So that's the inherent efficiency of diesel power. The turbocharger was a free ride. What happened is you'd have an exhaust temperature out of the engine at about 1600 degrees. It would cross the turbo, compress that air. The exiting exhaust out of that turbo was probably 1400 degrees. In thermodynamic terms, that 200 degree temperature drop represented energy, and that's in essence the free ride that powered that turbocharger. On a theoretical basis, that's what was happening. So now instead of 34% efficiency, you bump that a few points, and that added to the efficiency of a diesel engine. I'll talk more about that later. The same time this wheel tractor scraper came out, the DW21 was introduced, same drivetrain and everything, except this had a 5 with a two-speed splitter. The DW21 was a 5-speed only, smaller bowls typically, smaller speed. This unit was 32 miles an hour. The 21 was probably in the neighborhood of 24, 25 miles an hour. Over the next 6-8 years, both of these units, the 2-axle and 3-axle, were upgraded. This was Caterpillar's final DW20. This was the 88E, and its complementary machine, the 21, went from the 8W to the 69C to the 86E. So this was the final show in the scraper line in the 50s. Direct drive, 345 horsepower, cable-controlled system. Now, the next thing is, what did you push these guys with? Here is in World War II, your main track-type tractor in the D8 class in World War II was the 8R, what they called the slide bar D8, and that was upgraded post-war to the 2U, which was about a 150 horsepower tractor, and they went from a slide bar to a forward-reverse 5-speed. A tremendous innovation in terms of ease to operate. This was the main dozer that existed early in the 50s. This was your main push tractor that got behind these scrapers. Some dealers took this tractor as well as the 14A, which followed it in 1955, upgraded to the D342 from the 13,000, same bore and stroke. Took these tractors and built what they'd call a high output D8. You've probably heard of them. They'd basically take a D337, throw about 100 more horsepower into a D8 to make it a big pusher, but the literal example of what happened is you had an engine with a tractor deteriorating around it. So it didn't work out all that well, but it illustrated the serious mismatch between push power and scraper power. So think about this. You're in a post-war fleet. The 50s are emerging and rolling. What's going on market-wise? Eisenhower signed the Interstate Highway Bill in 1952. So subsequently, over the next 4 or 6 years or so, engineers are working away, and by the mid-late 50s, these jobs are starting to come up for bid. The interstate highway system was all pioneering dirt. There was no rebuilding of existing roads. It was all new dirt work. So these jobs were literally 70% equipment and fuel and operators, and maybe 30% material, where today it's just about the reverse of that. So these were big jobs. They weren't that big in the 50s, but they were getting big. And when you think about the fleet that was available to handle that, not to mention the industrial market that was coming on and the mining market that was coming on, you had a hodgepodge of mismatched equipment for your earth-moving systems. You had high-speed DW20s packing 30 yards, maybe getting up to 30, 35 miles an hour, if you had the haul road maintenance to do it. What did you have to maintain a haul road? Maybe a 70D 99E number 12. What happened when you got the dirt to the fill? Maybe you had a 2U with a dozer dragging a 5x5 sheep's foot or something like that. you really did not have a very well balanced fleet to really get some production, and you didn't have a lot in the way of options to get there. Now, when you think about what needed to be done, everything was hitting the wall. Engines were 2-valve pushrod engines. Every engine in the Cat line had been stretched to the ultimate. The D337 was turbocharged. They had a very complex weight gauge pressure ratio control system on it. It was boosted so high that the response of the engine was very poor. All the other engines in the line were pretty well 2-valve, slow speed, mid-speed, non-turbocharged engines. So what had to happen is something had to take place very large, because everything relative to this equipment was obsolete. Engines stretched to the limit, transmissions, which were countershaft, direct drive transmissions, you couldn't build them any bigger. If you could, you couldn't find men strong enough to shift them. And then you had a cable control system that did all your controlling of your implements in only one direction, no positive down pressure. So that's what hit the wall in the 50s. Competitively speaking, you didn't have a whole lot to worry about, but it's sort of what it was. And as a contractor, you were faced with this dilemma of what I'm going to do. Now, you may have noticed I did not mention the D9, the 18A that came out in roughly 1954-55. And I'll take a little sidebar with this tractor. In my business with my people, I didn't really mention what I had done when I left Caterpillar in 1973 and formed a Peterbilt truck dealership in Casper, Wyoming. And over the next 35, 40 years, I grew that to an 18-location operation, primarily in the Northwest. Sold that out in 2014. So I dealt with people. I had roughly 500 employees. One thing I did in that business is we depended totally on innovation and idea generation for our success. So I reviewed with our people 3 levels of quality as I saw it. Level number 1, you have to provide a product of good, reliable quality that is available for its purpose. But when it is not available, you have to back it up with a quality system of service and maybe parts to make it become available again. But the reality of that's a barrier to entry. If you cannot do that quality level number 1, you're going no place. So when I was at CAT, there was a quality level number 2, as I define it, of give the customer what he thinks he wants. I'm not necessarily a proponent of that, but in the 60s, when I was at CAT, that was kind of a big theme. The problem with it is the customer seldom really knows what the hell he wants. He'll tell you what's wrong with the existing product, but what do I know? I'm moving dirt. I don't know what new innovation I should be doing. Which brings you to quality level number 3, as I see it. Give the customer what he hasn't even thought of yet. That, to me, is a top-end level of quality. And I bring this up right ahead of talking about the 1889 because that's kind of what happened. In those days, in the 50s, trust me, engineering ran that company. And I'd almost say that with the addition of thank God. Had the D9 18A been introduced with the marketing department that CAT had in the 60s, they would have probably quashed the project. And let me tell you why. That 18A, Caterpillar started building that tractor. The engineers took it on for the simple reason that they now had a 6 1/4 bore, 6-cylinder turbocharged engine capable of 270 horsepower. So they looked at that and said, bingo, we've got the power, let's build a tractor around it. And that's when the 18A D9 emerged, was in that mid-50s era. It was a big, frankly, kind of a clumsy dinosaur of a tractor. When you pushed scrapers with it, the gauge of that tractor was so wide against the hodgepodge of scraper equipment on the market in those days, and they were narrow, tall, long bowls. That D9, the undercarriage, would work like that because the width of the scraper bowl was narrower than the gauge of the tractor. And you can only imagine what that did to undercarriage wear. Secondly, it was a direct drive tractor, big and clumsy and hard to shift and maneuver as an operator. But it had a third kind of a unique problem to the typical contractor in the early 50s. It was a 270 horsepower tractor. The rule of crawler track type tractors is a weight to horsepower of 250. In other words, if you build a tractor that weighs 300 pounds per horsepower, it's doggy. If you go under 250 horsepower and build one that's 200 pounds, all you do is spin the track. So the magic number, if you look at any track type tractor, the ratio is always 250. So that meant this D9 weighed about 70,000 pounds. And along with that, what did the typical contractor have for haulage equipment? Maybe he had an 8-foot wide tandem axle lowboy with a beaver tail on it and a fixed gooseneck, pulled with a tandem axle, who knows what, Ford or something. All of a sudden, here's a 70,000 pound tractor, and he has no capacity to move that thing around. So, what really happened when that tractor was introduced and brought out, it was an extremely successful entry. And in my opinion, the reason it is Caterpillar has come out with this tractor. The experts in the industry, I've got to have one. And that's what took place. D9s were every place. Logging used them, construction used them, industrial applications. It was an extremely popular tractor. You can even find them in northeastern Montana up on the High Line, still dragging discs and plows. 1889 still working up there. So I mention that as an introduction to what happened next. Here we are emerging, everything is stretched to its limit, and something had to be done. A new clean slate of paper had to be drawn. First of all, you had to figure out some functional specs. Here's the market. Here's the size of these jobs growing. What do we want? And fortunately, again, engineering, they set up an idealistic system of equipment that was flexible but had ultra-high productivity. It then kind of went backwards, and everybody said, what do we have to do to get there? Well, it took 5 things to get there. I got a phone ringing here. It took 5 things to get there, and I'll go over each one as I proceed here. First one was power. You couldn't go any place without power. Nothing could be developed or built if you didn't have the power to pull it. So here you had an engineering system. You had drivetrain engineers, you had mainframe engineers, and you had engine engineers. These functional specs started to come up. And these people told the engine people, here's what we have to make this system work. We need a 400 horse and we need a 500 horsepower engine. We need a 700 RPM operating range. And in that operating range, we need a torque rise of 25%. Now, I'll guarantee you in engineering terms, your chief engineer in the engine department, you look at that, and by the way, we don't want it to weigh over 9,000 pounds. When you're faced with a task like that, I can't imagine what that engine group thought when that came forward. But you got to remember 3 things about Caterpillar going into all of this, 3 features of this company. Number 1, Caterpillar was a wealthy company, very profitable and a standalone balance sheet, top end in their industry. Number 2, they had a deep engineering bench. Caterpillar engineering was the best in the industry. So that was in place. The third thing Caterpillar had was a superior distribution and dealer organization. So once this equipment got into the market, it could work and be supported and provided for. So I'm going to go through 5 issues here. The first one is power. Now this happens to be 3 of the 5.4 by 6.5 engines that came out of that late 50s analysis. I found, this is part of my collection, I found examples of all 3 of those engines, took them out of scrapers, got them running, mounted them up on trailers for show and tell. There's 3 of them. They are 5.4 by 6.5 bore and stroke. You do the math, that's 2.5 liters per cylinder. You had a 4-cylinder 10-liter, a 6-cylinder 15-liter, and a 90-degree V8 20-liter. That was the line. The first one was a D340, 4-cylinder. Frankly, not a terribly successful engine. It was naturally unbalanced, so it had to be counterbalanced. It was sluggish. It was highly boosted. It found only one home, and that was a 619 scraper. When that scraper was discontinued, the engine was dropped. The second engine in the lineup, which was the real super success of the line, was a D343. This engine was in everything, and I'll describe a bunch of them to you. But it was also, as a secondary application, used industrially. And it was also, some of you may know, the 1693 truck engine. This was the baby. Here's another view on the other side of that engine. But what I'll really bring the focus on this engine line to is an engine nomenclature of the RM180. The 3 engines were the D340, D343, and the RM180. You'll hear this engine a lot termed the D346. That was terribly unofficial. The background of this line and nomenclature was that this engine, this family, was the last purpose-built engine group Caterpillar ever did. These engines were strictly built for Caterpillar wheel-type equipment, so they had a bunch of very severe design characteristics about them. First of all, they were heavily webbed in the block, and had huge bearing surface area. So they were massive engines, which made them terribly expensive and heavy for other applications. But for what they were doing, bouncing around in scrapers and wheel dozers and everything else, they were physically very stout engines. I mentioned to you what they had to do in terms of torque rise and horsepower settings. So what happened, you had the D340, D343, RM180, which was not available anyplace. This particular engine ran at 500 horsepower. The 6-cylinder ran at 400. How do you take an engine of this displacement, 20 liters, and get 500 horsepower out of it? Do the math. That's 2.5 cubic inches per horsepower. And I told you how heavy this engine was. It was extremely heavy, but it weighed 12.5 pounds per horsepower. You remember that big World War II V8 I told you, and I asked you to remember 90 pounds per horsepower? That wasn't that long ago when this guy came out. So how do you ever get that degree of horsepower coupled with performance out of this much displacement? Mind you, I told you 500 horse, 700 RPM operating range, and a torque rise of 25%. You do it, number one, with aspiration. So this engine had a very significantly large turbocharger on it, spun at 90,000 RPM. It was capable of producing 3 times atmospheric pressure. Now, mind you, at sea level, atmospheric pressure is 14.7 absolute. So the intake manifold air pressure in absolute was 45 psi or 30 psi gauge. Another thing happens when you heat air or a gas that quickly to that degree of temperature. Natural gas laws says you're going to generate heat. So what happened between the turbo and the intake manifold of this engine, that gas rose to 425, 450 degrees under full lug. When air is that hot, the molecules are moving like crazy, and you can only get a small quantity of air molecules in a cubic inch. So that air had to be cooled back down. This was one of the first engines, this family, in the Caterpillar line that took that air and reduced the temperature, in this case with a jacket water aftercooler, which was in essence a radiator cooled with jacket water, 200 degrees. That air was forced over that set of fins and reduced from about 450 to about 250. So the number of molecules per cubic inch going into the cylinder of this engine was drastically increased. And you can understand, to get more fuel to burn, you've got to have more air molecules. It's a very, very exact ratio, air molecules to fuel molecules. If you don't have the air, you can't burn the fuel. You can sure pump in more air, but if you don't put in more fuel, nothing's going to happen. The third thing that happened on this intake system is this little device right here was known as a pressure ratio control valve. And what that valve did was sensed when the air intake pressure was 3x atmospheric pressure. This valve would open and would wastegate exhaust gas around that turbocharger. A very important point. I told you that the engineers demanded a 25% torque rise out of this engine. Typically, when you boost an engine, highly boost an engine, the torque curve is very flat and the operating range of the engine is very narrow. Displacement tends to mean everything in terms of torque rise in engines, but Caterpillar got around that in a very unique fashion. Literally the first time it had happened. It had been tested on the 8080, but it really came into practice with this family of engines. So what they did is they matched the turbocharger to achieve full pressure at full lug. I told you 700 RPM operating range. High idle on this engine was 2300. Full load, when the rack is all the way open and its full power, was 2100. Full lug, peak torque, was 1400, so you had a 700 RPM operating range there. The turbocharger was matched to 1400, not 2100. But that presented a problem. First of all, that's how you got that massive torque rise, is you had the air and the fuel at 1400 to do it. But as the engine would ramp up to 2100, that turbo would keep spinning, and two things would go wrong. One, you'd overspin the turbo, and two, you'd overboost the engine. So what happened here is you'd build air pressure up to 1400 RPM, and then you had a level pressure from 1400 to 2100 of 30 psi in that intake manifold. I'm giving you a kind of a complex answer here, but I do want you to understand what a serious innovation these power plants were. It was a massive improvement in power and really carried this line. Without these engines, nothing would have happened. Now, to describe it again on a little more technical term, to give you an idea what's going on internally here, engineering and engine engineering has a term called BMEP, brake mean effective pressure. What is BMEP? That is the average pressure in PSI on top of the piston throughout the power stroke, from top dead center to bottom dead center. You can calculate it quite easily. You need to know the torque output of the engine, the displacement, the RPM, and you can figure BMEP. A naturally aspirated engine that sucks in an air load on the intake stroke, you are limited to the number of air molecules you get in. Doesn't matter how much fuel you dump in, you're only going to achieve a BMEP of 81 psi. This engine ran at a BMEP level of 240. I hope you appreciate what a differential in power output that represented in this design. So what happened here is we dumped in more fuel, 3 times more fuel, 3 times more air molecules to get 3 times more horsepower. That was the secret of what happened here, but it presented a number of other problems that I'll get into. To show you the uniqueness of this particular engine, this is a backside of that RM180. 13 gears in the timing gear train. I'm trying to impress on you that this was a purpose-built engine. You would only find this engine in Caterpillar wheel tractor scrapers, period, which meant they only built 225 of these per year. This is a single casting that fits on the backside of this engine. 13 timing gears in it. You had 4 camshafts. And this engine was parallel ported, which means you had a row of exhaust valves and a row of intake valves parallel ported. Air came in up and down that way. Exhaust, same thing. It split apart from those cylinders. Very efficient breathing, but it had to be driven. So your starting point, you got 4 camshafts to power. Then you've got fuel injection pumps to power and engine oil pumps to power. This engine had a parasitic load of 12 items. You know the big ones. A 40 horsepower fan. You had a big alternator to drive, air compressors, cushion hitch pumps, fuel transfer pumps, transmission pumps, and then the big kahuna fit right here. I blocked those off to support the air cleaner, but what sat here was a pump that could absorb 270 horsepower, which powered the scraper, obviously. And what I would tell operators, when you're in the cut, just put that thing in neutral, rev it up to 2100 so you can get full performance on those hydraulics, and not added benefit, you don't grind up your tires. That's the absorption load that this engine had. But what I really want you to see is the custom nature of the build of this engine. All these ports that you see were custom set up strictly for scrapers. So that's item number 1, and I got 4 more to talk about. What do you do when you've got that much power coming into a system? You've got to distribute that power. And believe me, counter shaft, direct drive, hand clutch drivetrains are not going to handle it and not going to work. Caterpillar, and this was a real genius of the company, went to epileptic gearing. That's a fancy word for planetaries. And when I got to learn about planetaries, you learn just how magical a planet set is. And I'll try to describe, I'll give you a 10-second lesson in planets. If you've got a D9 tractor, you have 5 planetary gear sets lined up in that transmission. A planet set has a sun, planet gears around that sun, and a ring gear that encloses the whole thing. Planets work by putting power into one unit, taking power out of one of those 3 units, and restraining one of those 3 units. In Caterpillar power shift transmissions, they did it by restraining the ring gear. So you put power into all 5 of those planets, and if you wanted first forward, you closed the forward clutch and speed number 1 clutch. All the other ones just sat there and spun, and power went out those 2 drives. If you shifted up to second, you just dumped 1 clutch and engaged another. I'm going to go quickly on that because it can get kind of messy and confusing, but just trust me, planets had some major, major advantages. The gears were loaded in 2 places, so you had no side loads on the bearings. A D9, for example, the clutches on those ring gears were 22 inches in diameter. You could do that with a 1200 RPM engine without too much tip speed, and so you didn't smear those clutches. But you could shift, you could take one of these 66A D9s you see out here, and you can shift that from 3rd forward to 3rd reverse, not decelerate it. You will get some modulation. And that tractor, if the driver can stay in the seat, can do that all day long. And you will not injure that unit. It's not necessarily good practice, but that's how strong it is. Power shift planetary gearing would outlast direct drive 3-to-1 in terms of life. Then item number 3. Cable was obsolete. You had to avoid and get away from cable controls, which meant hydraulics. I showed you a picture of that 14A, had a single drum cable control on the front and an Atico hinge type ripper on the back. That ripper ran with a hydraulic pressure of probably about 1,500. CAT determined that what they had to have to make this equipment perform was a 2,500 PSI system. Nobody had done that. CAT designed all the hose. They came out with a product called XT3 hose. They designed the O-ring system, which is what sealed joints that were bolted together. They developed a completely closed hydraulic system and had no vents, as did everybody else. It was closed, and the reason they had to do that is everything was machined to such fine tolerances for those higher pressures, all the valve packages and everything. And then the big thing they did was went to a vane-type Vickers pump, which was a very efficient pump that would compensate for wear throughout the life of the pump, so you had a very even hydraulic performance until pump failure. Everybody else used a gear pump that would just drift off in performance. Now we'll get into item 4, which is a category I kind of call the other things. Smaller things, but critically important. Number 1 was metallurgy. Think about this. You've got a cutting edge in the center of that 657 frog. You got 3D9s pushing on you. That cutting edge hits a 4-foot rock and everything stops. 1,500 horsepower is dumped onto that cutting edge, and most likely it does not break, nor does the hardware holding that cutting edge to the frog. That took some serious metallurgy. They call it GET, ground engaging tools. You had to balance wear rates, hardness, ductility, and brittleness to make sure you had componentry that could live and wear. Think of a ripper tip on a D9 tractor, 4 feet in the ground. You don't rip dirt, you rip rock. And all of a sudden, that ripper hits a rock, and the front end of that D9 comes 2 feet off the ground. Going through that rock, that tip got hotter than blazes, and then it received a severe point load of the entire forward force of that tractor, and likely did not break. That takes some serious metallurgy. Another example, and I'll get off, is a dozer blade on a D9, or excuse me, a dozer push arm. Think about 50 degrees below that you run into in places like Canada. How do you build that push arm so it's strong, yet when it gets to that degree of coldness does not snap via brittleness at that temperature? Caterpillar figured that stuff out. We don't think about it very much, but that's what it was. Second item they had a real handle on was welding. Caterpillar literally wrote the American Welding Society handbook. You pour through that handbook, which we did in mechanical engineering, everything was footnoted Caterpillar. They either developed, invented, or drastically improved virtually all popular welding techniques, MIG, TIG, submerged art, and then they built their own, which was called an inertial welding system. So you could take 2 items, rotate one, hold the other one still, ram them together, and bang, they were welded up. Heat and pressure. CAT invented that. Next thing I'll mention is oils. Caterpillar came out with a Series 3 oil, and I'll explain what happened here. Engine oil has 4 purposes. Number 1, to lubricate, that's obvious. Number 2 is to seal. When that piston is going up and down in a cylinder, somehow you have to seal that explosion to where it doesn't bypass the rings. So you got a compression ring and an oil control ring on a piston. So 2, it seals. 3, it cools. All engines internally develop a ton of heat, and the only way to expel that heat is through oil as a coolant. So all CAT engines you've probably noticed have oil coolers, either air to oil or coolant to oil, to cool that liquid. I mentioned a 240 BMEP 343 and RM180. You're pumping 3 times the air, 3 times the fuel through that engine. So guess what? You're developing 3 times the fuel soot. Fuel soot is nothing but unburned fuel. And when you're highly turbocharged, the fuel is definitive, the air volume is a variable. So a lot of times you don't have a balanced ratio of air to fuel. So fuel, result of that is fuel doesn't get burned. Where does that soot go? Up the stack or down into the crankcase? Series 3 oil, 1 gallon of Series 3 oil could absorb the fuel soot developed by 200 gallons of oil. So if you, for example, today see a truck with a 10-gallon crankcase capacity, that means that truck can drink 2,000 gallons of fuel, and you've got to change the oil. If you get 6 miles a gallon, 12,000-mile oil change interval. That's how all that comes up. You can credit Caterpillar for developing that oil. They were not in the oil business, but they had a problem and they had to solve it. So their own scientific evaluation of oil produced an oil spec, and I still remember it, I don't know why, MIL-L-2105 CD. So any oil you look at today will carry that CD rating. And that means it's an extremely high detergency, probably a 1540 variable viscosity oil. And then CAT permitted you to dump it into everything. Engine, transmissions, hydraulics, everything but the final drives. The last thing I'll mention in this category was a device called a soil bin. And it was a tabletop trough of specially prepared and compacted soil. And what they did was built models of scraper bowls, models of bulldozer blades, models of buckets. They'd pull those things through that soil with strain gauges, and metering could tell how much force was required to move that dirt with that particular device. How many horsepower per cubic yard or inch of cutting edge or whatever you want to measure it by. It was a very inexpensive, rapid way to optimize designs. And I'll point it out in a little bit, just some of the results of that soil bin test. That covers 4 items. I mentioned there was 5. So what was number 5? And this was a problem that really didn't get solved, but was modified to the point that it was workable. And that topic is tires. You got 2 types of tires in rubber-tired equipment. Loader-dozer tires, and the way you solve that is you just made the tread deeper and deeper and deeper, depending on if you were in rock or dirt or what. And then you just grind them off. Haulage tires were a whole different problem, because the enemy of a haulage tire is heat. If you think of a round tire, and as that tire rotates and it hits the ground, you've got a flat spot. So the radius of that tire would go from, call it 4 feet, to where it hit that flat spot, and that radius would suddenly shrink to maybe 3 or 4 inches. That generated heat. That point was working and working and working. And when tire internal heat got north of 375 degrees, you had a serious problem called tire separation. Caterpillar had to address this. They didn't want to get into the tire manufacturing business, but it sure got them into the tire research business. Dr. Tire at Caterpillar was a man named Charlie Sons. I listened to Charlie forever on these topics. He was the guy that really understood tires and how they worked and how to fix the problem. He developed a scale in tires called ton-mile per hour. Every tire, most notably if you really had a problem, you went to a radial tire, which had radial steel around the circumference of the tire and didn't squash when you hit the ground, quite like a bias ply tire did. So it could stand a higher ton-mile per hour rating. Say, for example, you've got a tire with a TMPH of 480. What that meant, as an example, pick a number. You're going to drive that scraper a distance of 20 miles in 1 hour. That means the average load that you can carry on that tire, loaded and empty, is 24 tons. 24 times 20 equals 480. You've now hit the limit of that tire. If you want to go further, you got to carry a lighter load. If you're going shorter, you can carry a heavier load. If you exceeded TMPH, you were going to fail that tire, period. It might not fail that day, but the next week it was going to unwind on you. The tread would separate. So one of my biggest jobs in consulting with people was immediately looking at their application and figuring the TMPH so they didn't get into trouble. Tire costs can kill the profits on a job. So I went through those 5 items. The brilliance of Caterpillar engineering, and I truly mean that, and that's what I really want to emphasize to you with this talk, is to give you an impression of just how deep the skill set was at CAT to do that. Here's what came out of all this. And I'm skipping the small stuff. The smallest scraper I'm going to talk about is a 630 D343 at 400 horsepower, 29.535 rubber, a 21-yard struck, 28-yard heaped scraper bowl, 42 miles an hour. This was literally the smallest in the line. This tool weighed 75,000 pounds. The next in the lineup was a 631, same engine, same bowl, 2128, 400 horsepower, 2-axle, top speed, 32 miles an hour. Much more flexible unit. You could handle a whole lot different terrain. It was not necessarily a long haulage unit like the 3-axle was. Obviously, it did not have the tire capacity with 4 tires versus 6, so you really had to watch TMPH on this machine. Next in line was a 632, completely similar to a 630, except it had a 28-38 bowl. That was the only difference. So the weight to horsepower ratio of this unit got into the high 400s. When I tell you the entire line of Caterpillar equipment, from the 630 to the 666, you got a 666 you can look at down here. The 630 weighed in at about 75,000 pounds. The 666 about 125,000 pounds. The net to tear ratio on all cat scrapers was about 1.0. In other words, that 666 weighing 125,000 typically packed 125,000 pounds of dirt. 250,000, 900 horsepower, do the math. That tractor scraper outfit came in at about 270, 280. This guy came in at about 480. So obviously it was strictly a flatland, very doggy performing machine, hard to get it moving and up to speed. Strictly a long haul, high capacity, easy conditions. Did not sell at all well, was dropped 2 years after introduction. The next was a 641. This was the smallest wheel tractor scraper with the RM180 at 500 horsepower. 33.5, 39 rubber, 28-38 bowl, 32 miles an hour. Very popular machine when it first came out because the weight to horsepower was down in the low 300s. Next was a 650. You've got a 650 down here that John has, and you can take a hard look at that. I'm going to use this scraper bowl as an example to talk about that soil bin again. Take a look at the bowl on any of these hydraulic wheel tractor scrapers. And then take a look at the bowl on those pull-type cable scrapers. The pull-type unit had a narrow width of cutting edge. It was a very deep bowl, had very high sidewalls, and the cutting edge was way forward. What that meant is that dirt had to move all the way back into that scraper bowl. As it moved in, it had to compete with the dirt that was already in there. It took huge horsepower to stack that scraper bowl. And as you lift it and move it, that takes horsepower. What these bowls did, the cutting edge, instead of up here, was moved back almost halfway to the back of the bowl. The wall of the scraper came down, the width increased, Notice the curvature on the apron. So what would happen is you'd start loading this thing, the dirt would stack up here, and then what would happen is that dirt would mushroom, move forward, and backwards, but it didn't have to lift very high. That design permitted a new standard in loading. If you've got nothing better to do, go down here and watch some of these track-type tractors pulling a cable scraper and just time how long it takes to load them. If you properly matched the push power to these scrapers, we had a standard. And if you didn't meet it, you either needed to train your operators, your cut boss, you had a mismatch in push power, something was wrong, because all Cat scrapers could load in 30 seconds. That was the standard. It was a massive improvement in productivity. The 650 ran at a weight to horsepower ratio in the low 400s, high 300s. The 651, same machine, 2-axle, 32 miles an hour, RM180 at 500 horsepower, 32 44-yard bowl. Next in the lineup was a 657, excuse me. John has got a 46M sitting down here ready for restoration. That was this identical machine. I don't know if you got another one around here or not, John, but anyway, he had the latest and greatest in 657s. D343 in the back, 400, RM180 in the front at 500, 900 total horsepower. This machine had a 44 54-yard bowl in it. Weight to horsepower ratio could get under 300. Top speed 32 miles an hour. Extremely popular machine, especially when the push-pull option came out. The next one was a 660. Not an especially popular bowl. You see an awful lot of equipment that said 660 on the tractor and 650 on the bowl instead of 660. The bowl was awfully big. A 44 54-yard struck and heap bowl. Again, very high weight to horsepower up in the upper 400s. And then the big daddy of the fleet was at 666, 500 in the front, 400 in the rear, 37.539, 37.551s in the back, 44 54-yard capacity. 42 miles an hour. This was an incredibly high-performance machine, weight to horsepower of about 290,000 pounds. It was a performing unit as long as you had a big enough job, a long enough haul, and enough push power. So, what's next? Talk about push power. There's a team of these guys down in the demonstration area here. This was a dual D9, 266A D9s, 385 horsepower for 770 horsepower. This thing weighed 180,000 pounds, so you could almost develop a pushing effort of about 140,000 pounds. It was a very popular unit if you were a big contractor, if you had big scrapers, and if you had deep pockets and enough work ahead of you to keep this stuff working. One operator, so you cut the cost of 2 men, joined together so the hookup time behind a scraper push block was very quick instead of having 2 separate tractors that had to mate up and get going. But if you had a good set of skilled operators, that tended to not be a problem. Where this guy really came in is if you had a 666, 657, and you needed to triple push it to get your cycle time straightened out. So you got 3 D9s. You typically put the single 9 in the front and get behind that single with this set of dual D9s. Reasonably popular tool. Next, if you had a pile of rock on your job, out came the 769 truck. Guess what it was powered with? D343 at 400 horsepower. Trucks were a little bit unique in that you could get a net to tear ratio of about 1.3 versus 1 to 1. This was a 35-ton capacity. It was perfectly matched to a brand new wheel loader called the 988, the 87A. A marvelous machine, articulated obviously. this was one of the finest wheel loaders of its day. This was the father of all these new loaders you see out here. This was the concept machine. This was a horse. It was extremely reliable, extremely well balanced, extremely well engineered. It was matched 3-pass to the 769. Bucket size ranged from 5.5 to 6.5. So now you've got a fill to worry about. 3 pieces were available for the fill. 824 wheel type dozer, D343, 300 horsepower. Very quick, very efficient in managing fills. You could also get this machine in a tamping foot compaction system. This foot, again, a product of the soil bin tests. This was a high-speed, high-production compaction unit. If you had a really big fill, you used an 834, 400 horsepower Big Brother. And then, of course, you had to get this equipment between the cut and the fill. It was critical with this high-speed gear that you maintained haul roads. You had to do that. These heavy, high-speed scrapers would literally pound a haul road apart, so maintenance was very critical. 150 horsepower, 14E power shift. Big Brother was the 16, the 49G. D343, 225 horsepower. A massive, huge motor grader that could really keep that haul road in good condition. So there you have it. I hope you have an impression of the severity and magnitude of the change that occurred at Caterpillar from the late 50s to the early 60s. I consider it the most massive change in Caterpillar history, maybe slightly second to the evolution of the diesel engine in 1930. This system, to me, was a hallmark of conversion of this company. I'll make 2 final remarks about this system. Number 1, if you were a dirt contractor in this period of time, you wanted to be low bid and you wanted to make money with that bid, you had no choice but to buy a new fleet of Cat equipment. It was a marketing dream. I'll also make a second remark that kind of addresses Caterpillar's worldwide position. 1966, Cat did 45% of their volume outside the United States. You could say 3 things about the world market. Whether a foreign country loved us or hated us or somewhere in between. And maybe they even had a policy they will not buy anything from that darn United States. But you could rely on every country in the world breaking the rules and buying 3 things from the United States: Boeing airplanes, IBM computers, and Caterpillar tractors. Thank you very much. Any questions? I probably wore you out. Thank you.